All right. Welcome, everybody, to Paleo Talks, episode 12. It's hard to believe we've been going for that long, once a week. I do want to let everybody know that next week we actually will not, since it's a holiday. So episode 13 will be after next week. This week, we have Dr. Michelle Stocker, and she is pretty close to us here. She's actually up at Virginia Tech, where she's an assistant professor in the Department of Geosciences and also the Global Change Center. And she's going to talk with us about one of her research areas, which is amphibian research, in particular frogs today. So this is really exciting. Thanks for being on the show, Michelle.
Thanks so much for inviting me. This is going to be fun.
Yeah, it's going to be really, really cool. David, you want to introduce yourself so you can tell everybody about the show a little bit too?
Sure thing. As always, I'm David Moscato. I'm the Gray Fossil Site Science Communicator and the guy in the chair for our Paleo Talks events. Once we get started, Blaine's going to lead Michelle through talking about this research, ask some questions. Mostly we're going to hear from our guest as usual. And then about partway through, 20 minutes in or so, we're going to open it up to questions from the audience. We are streaming live on YouTube, so if you are joining us on the YouTube video, you can type your questions in the chat off to one of the sides of the screen. If you're having trouble for any reason getting your question into the chat or you can't log into the chat, head over to the Gray Fossil Site Facebook or Twitter page, send us a message on there. I'll be keeping an eye on those as well. And then about 30, 35 minutes, we'll end the recording, but we usually stick around afterwards in case there are extra questions people have.
All right, thank you, David. So I'm Blaine Schubert. I'm the director of the Center of Excellence in Paleontology, and the show Paleo Talks is coming to you from Johnson City, Tennessee, East Tennessee State University. And again, this talk today, well, the title is A Ribbiting Discovery in the Triassic. And the Triassic was a long time ago. It was way back when you're comparing us to the Gray Fossil Site here, which is about 5 million years old. We're going to learn about a site that's much, much older. And so, Michelle, if you could just start by introducing yourself a little bit more, also maybe where you got your PhD, where your background comes from, and then about your position there in Virginia and the lab that you have.
Sure. So I'm an assistant professor of paleobiology in the Department of Geosciences at Virginia Tech, and I've been here since 2014. Before that, I did my PhD at the University of Texas at Austin, working in Chris Bell's lab. And what was really nice about working in that lab was that we weren't focused on any one group of animals or one time period. So the lab group when I was there was made up of students who worked on skate and shark evolution and fish evolution and ossification patterns and amphibians and mammal teeth in the Quaternary. And so we got to hear so many different types of research projects being worked on all the time. So it was really a good kind of broad background for being able to teach undergrads now at Virginia Tech. Before that, I did my master's at the University of Iowa with Chris Brochu. And before that, I did my undergrad at the University of Michigan. And I was a geology major there, but really only because I was a work study student that worked in the fossil prep lab with Bill Sanders. So my background kind of begins with fossil preparation and getting things out of the rock and understanding, how things are preserved in there in the first place.
Fantastic. That's really inspirational for a lot of people, I think, to hear those stories. And for us, it's so exciting to have another program in this region. I think when you guys went to Virginia Tech, there wasn't a paleontology program.
There was not a vertebrate paleontology program, that's right. So when Sterling and I started here in 2014, we were the first vertebrate paleontologists. There had been an invertebrate group here for a long, long time. Shuhai Zhao is our invertebrate paleontologist, and Richard Baumbach had been here for years before that. So there's a long history of kind of paleoecology and really early life paleos. Shuhai's research is in the Ediacaran, which right. is like you talk about going from the gray sites age to back to the Triassic. Like we're talking lab group meetings about fossils that are 700 million years old, which blows my mind. So very, very, very old.
Yeah, for sure. Well, if we could go ahead and get started with you sharing your screen, then we can start working through your slides.
That sounds good. So I'm more than happy for you to ask questions, whenever, and just interrupt me for what I'm doing here. And we'll do this one. Sure. There we go. All right. Because nothing can be easy, and I can't see my notes on my laptop at home. Now I have my talk in 3 places. So, all right. So, like you were saying with, we've got Paleo at Virginia Tech now, but this is kind of new, and we've built our program for the Paleobiology Research Group at VT on collaboration and really involving undergraduates in our research. So the work that we do really can't happen without the undergrads, especially the undergrads, but also the grad students that work with us, and then our awesome collaborators. And for this project in particular, we were working with researchers from the University of Florida, so Dan and Dave, and then our group from Petrified Forest, who I've had research connections with since 2003. So working with Bill Parker, and then more recently Adam Marsh, so that we can, really have a good understanding of the fossils in this part of the Southwest, and make sure that those fossils are preserved for everybody to be able to look at. It's awesome to be able to work with the National Park Service on this stuff. So all of our students, normally we would have been coming back from the field right now and collecting more material from Arizona. This year that didn't happen, but we've got plenty that we can still work with. But everybody here, including the little field baby there in front of the excavator, have been collecting fossils to help build this story. So we can say a lot more about what's out there based just on the work that everybody else is helping us with. So I think last week you all talked about the Cretaceous, if I'm not mistaken, maybe 2 weeks ago with Dr. Stephanie Drumheller from UT Knoxville. So here we are at the end of the Mesozoic. So if we're looking at geologic time, our life today is this truck that's up on the top and we're driving along on the surface. But going back through time, the Cretaceous is quite a while ago. As Blaine said, we're going even further back here. We'll go down to the Triassic, and this begins about 250 million years ago when the Permo-Triassic mass extinction, and this was just terrible in terms of extinction on Earth. But it allowed a lot of diversification to happen within that Triassic period, because you basically hit a reset button and started over. Mm-hmm. So the way that we've been kind of looking at the Triassic traditionally is that there's these 3 components to it. There's these kind of holdover taxa, which I know Savannah Allred does not like me calling them holdovers, and I hate to do that. They're survivors from the Paleozoic. But we have a few species and clades that kind of continue on that we don't necessarily understand why, but they're still there through the rest of the Triassic. And then we have this big group of mainly reptiles, but not just reptiles at all, this indigenous Triassic fauna that's restricted to the Triassic. And this group of animals actually goes nuts. Like the Triassic is full of these species that you only find in the Triassic. And then at the end of it, almost all of them go extinct. And this group is super interesting. This is not a single clade. This is mainly the animals that I work on, because why wouldn't you want to work on something that looks nothing like what you see today? But they're mostly, many of them are within Archosauria, but they're on the crocodile side of the tree. So we're seeing these animals that look like dinosaurs or look like crocodiles, but aren't necessarily closely related and are only found in that Triassic period, just that 50 million year window. Then what's really interesting is that we start to see members of what we'd call the living fauna or the modern fauna, really early representatives of groups like mammals and amphibians, maybe kind of start to appear in the Triassic. And we get a few more of them, but at the Triassic-Jurassic boundary, traditionally, this is when their diversity has taken off and exploded. So the Triassic, I love this image from a kid's book that we have for our little guy, where the Triassic is this awesome, delicious sandwich bounded by these extinctions. And so all this interesting stuff is happening in the middle, but you need some way to bracket it. So our Triassic sandwich is what our lab group is focused on for a lot of our research. So I was saying, like, the modern fauna, or this living fauna that we have, kind of originates based on fossil material, but also based on molecular data back in the Triassic, somewhere within that period or at the Permo-Triassic boundary. And we get members of all of the groups of animals that are alive today appearing at that time. Most of them are from really fragmentary material or very small bodied specimens, disarticulated remains, or just bits of things that are hard to tell because they might not have the identifying features of more recognizable members of the group. So understanding the origination of all of these groups is something that our lab group works on pretty heavily. And we do that through our field work, trying to find early members of all these groups out in the Southwest.
What would a Triassic sandwich taste like? Like a phytosaur or something?
I think it would taste a lot like mudstone. I've eaten my fair portion of the Chinle Formation out there. It's a little gritty, it gets everywhere. Yeah, it's pretty messy sometimes. It's a bad idea to have it when it's wet and muddy.
Mm-hmm.
Yeah. So for the longest time now, most of what we've known for the Triassic period as a whole, that 50 million year window, has really been influenced by the fossils that we find in the late Triassic. And this is just that very last part from about 228 million years to 200 million years ago. So that's like less than half of that time, or just a little bit more than half of that time there. And it's mainly from the big fossils that are found out there. So large-bodied animals are pretty common at this time. There's some early members of dinosaurs, which you can see the Coelophysis kind of walking on the beach in the background in the picture here. There's a lot of these things that look like crocodiles, and those are the group that I normally study. Those are called phytosaurs. They're not closely related to crocodilians, but kind of look like it. So they're like crocodiles or phytosaur mimics here. And then there's these other things that are more kind of in the front of the image there. The really armored guy on the right is called an aetosaur. And these are tanks, essentially. They're covered in these bony osteoderms, both on the top and on their ventral surface, and then down their limbs too. And they're herbivorous, which kind of explains why they're covered in these armor plates. And then the one that's kind of following after its lunch there is something called a rauisuchid. And these often end up looking like theropod dinosaurs or paracrocodilomorph members. These look like dinosaurs in many cases, or big carnivorous predatory animals. And so this is what we knew a lot of the Triassic from, is these things that could be like, 3-4 meters in length, very large body size. But if you look at the composition of an extant community or living community today, the majority of the animals that are found in that community are really small, or at least are under a meter in body size for sure. But we just didn't have a whole lot of information about them. So when we're looking at these groups, we're getting kind of a biased viewpoint, not just from the time that's represented, but from the animals that are represented as well. So we've been focusing on figuring out just one part of this late Triassic community and kind of faunal change called the Adamanian-Rieveltian boundary. So these are time divisions within the late Triassic where we see some species level turnover in the fossils that are preserved there. And if you look at what's preserved at this time, then there's kind of this traditional Adamanian fauna. And then above that in the rocks, there's this Rieveltian fauna. But looking at these kind of two groups, they look pretty similar, right? There's still these crocodile-like things both below and above the line, these carnivorous looking things below and above, and those armored aetosaurs below and above. There's a few differences, but not a whole lot. So it's species level changes that are there. But again, everybody or almost everybody that's on this image is pretty huge. There's a person for scale. That's Bill's silhouette over on the side there. So you can get a sense of just how massive some of these animals would be. But we want to find out some of these smaller animals too. And so amphibians are a huge part of our extant community. They play important roles in the ecosystems. And of the group today, there's 3 major divisions that people generally know. There are frogs, which looks like our typical frog here on the bottom left. Salamanders, which are pretty diverse, both around us and then around you guys at ETSU, this whole kind of Southeast US has a high diversity of different species of salamanders that are so fun to go see after a night rain. And then there's this other group that's a little bit more cryptic called caecilians, but those are not worms, they're not snakes, they're another kind of amphibian. But all of these groups, or all of these members of this group of amphibians, is part of that kind of Triassic radiation of that modern fauna. They all today have fairly small body size. They all started at fairly small body size. And so today I want to focus more on just the one member of this group that we've been examining, and give it away with the title and everything for the talk today. We know we're talking about frogs. So when do frogs originate? What did the early frogs look like? So we had some sense of what early frogs look like from research for a while. There's Jurassic frogs called Procellaris, and this is collected from the Navajo Nation, and it was published in mid-90s. This is about 185 million years old, so this is much younger than the sites that we're working in. The Triassic ended at about 200 million years ago, and so this is like 15 million years later, right? You can see that it's fairly well preserved. There's a lot of material here. It might not look like some understandable bits at all, but can you see my mouse there?
Yep.
Awesome. So you're looking at the top of the head here. Frogs have this kind of T-shaped bone. This would be towards the front of the face. This is the back of the head here. There's some parts of the arms and legs. There's part of the pelvis that's in here. Some vertebrae. It's a nice kind of spray of the skeleton, I suppose. It could always be better. You always want more information, but there's a lot that's there. And so when this animal was published, this was proposed to be the earliest jumping frog, which is super cool, because the fossils that we're finding, you don't want to just find it as like, oh, hey, it's an early member of the group. Like, all these animals do things, right? And they do really interesting things. And we want to know when this type of feeding began, or when this type of movement began. So when did hopping begin in frogs? With the way that the bones are preserved here, they were able to see the movement of the hip joint on the vertebrae, and propose that, at least by 185 million years ago, frogs could do their typical frog jump, frog hop. But that's 185 million years ago. So do we have frogs in the Triassic? Yes, kind of. There are stem frogs that are from the earliest part of the Triassic. So I always thought this was just amazing that you've got these frog fossils from 250 million years ago. This is an animal called Triatobatrachus, and it looks awesome, right? The fossil itself is over here on the right, but you look a little bit more closely and it's actually mostly an impression. So it's mostly negative space in a rock. So you can fill that in, with latex or plaster or something, and get models of the bones, or use CT data, which is what we do a lot for fossils, try and reconstruct the morphology of the animal. But there's not a whole lot of actual bone material there. But from what is there, we can see an articulated skeleton. And this is one of the earliest members of the group. But what's interesting about this frog is it's got a really long backbone. So it's a much longer bodied frog, kind of more like a salamander almost. And then it has tail as well. So frogs today don't generally have tails.
So if you're going to find one bone of a frog, what bone would you want to find?
Well, to just give it away, I would want to find the bone that we found. There's a lot of frog skeleton, at least a modern frog skeleton, that's pretty recognizable as frog. Vertebrae are pretty distinct, and a lot of the skull bones are. But think about the way that a frog is kind of put together. If anybody ever did frog dissections in high school or in middle school, then you know that a frog is like, there's some kind of bony supports inside, but it's sort of just a squishy bag. There's not a lot there, and it's pretty small. And so you might have some really informative features of the skeleton to help you say it's a frog, but getting those preserved is really difficult. The part that we found, and just to kind of talk about it ahead of time, there is part of the hip bone. And frogs have really distinctive hips. So their hip is 3 bones normally. There's the ilium that's on top, and then the pubis and the ischium are the 2 lower elements there that form kind of a triangle. And we found that an ilium of a frog, which there's nothing else that looks like that. It's really distinctive. And especially the one that we found, it's very recognizable as a frog because it looks pretty similar to those of living frogs, or at least those of some of the living frogs. So we're able to identify that right away. And then it's a little bit sturdier too, because this is a bone that's connecting the legs to the vertebral column. So it's a little bit more robust. It's nothing like some of the, metopusaurid amphibians, like the big amphibians we normally find in the Triassic. But if we were going to find something of a frog, then that was the one that we could recognize at least.
Perfect. I don't want to rush you, Michelle, but we do need to move through some of the slides.
Sure, yeah.
To get to your main points here.
Well, I can skip ahead a little if you want as well.
Yeah, I would say go ahead and just move on through a little bit. And then as we get to the questions from the audience, you can use more of the slides and come back to them. But
sure.
Yeah, if you can skip to the next one where the ilia.
Yeah, so this is the distribution that we knew of frogs before. We had these two examples of early Triassic frogs. So two specimens or two species from about 250 million years ago, kind of spread out across Pangaea, or the paleocontinent here. And then that Procellaris specimen from the Navajo Nation is kind of equatorial, but also from like 65 million years later. So we had this huge gap, both in space and time, for what's going on in the evolution of this group. I have to have some nice fieldwork pictures in here to remind us of what we're missing. So this is what it normally looks like for us in May and June out in Arizona. Beautiful mudstones of the Chinle Formation. And we've been working a site out in this part of Arizona for 6-7 years now. And it doesn't look super huge. This is almost the whole site you can see in the picture. But we're looking for tiny, tiny little things in here. So you can see some little kind of bits of stuff in the rock. And we will sit out on the outcrop, here's Sterling for scale, breaking stuff open and looking at it in hand sample when we're outside. But then you can see those white bags that are on the ground near him and all of our toilet paper packages. So we bring a lot back to the lab and then prepare it here. We also do screen washing. And so that will often result in, a lot of teeth that are recovered. But the material from this site breaks down in water sometimes, so you get a lot of half teeth. So when we're looking in the field at these big chunks of rocks, we're able to see some nicer material, and then we'll actually keep it in the rock. So one of the things that we found out there was this ilium of the frog. So this is the specimen that we found. The scale there should tell you it's absolutely teeny. It looks like a little eyelash almost in hand sample. And we couldn't prepare it out of the rock because it's so small. So we CT scanned it with matrix on it still. So it still is embedded in its mudstone. But that allows us to see both sides of it without damaging it. And then by finding this specimen, we were able to look at some material that had been collected at other times as well and see like, oh, we actually already had some of this material from this area and just didn't recognize it for what it was. There's features of the element that tie it to frogs, so we can identify it that way. And then if we're comparing it with, oops, I think some of this stuff, there we go. If we're comparing it with some living frogs, you can see our frog, our Chinle frog there is on the upper left. The Jurassic frog is on the upper right, and it almost doesn't look as similar to that, but part of that is just because it's broken a little bit in the rock. But it's really similar to all of these in the yellow box, which are living genera of frogs. So we've already got a very froggy morphology going on by about 215 million years ago.
So if you already have something that looks very froggy, does that mean you have late Paleozoic frogs too?
Ooh, I would think so. I mean, I would really hope that they're there. Because if you think about like Triadopatrachus still looks, it looks kind of froggy. Like it's early enough that it's not exactly there. But that's at 250-ish million years ago. So, there should be some stuff. I'm not as familiar, unfortunately, with the Paleozoic record of these early potential frog specimens, or at least the early amphibian material, because you get it gets confusing, I think, recognizing which specimen belongs to a frog and which could be salamander, which could be some other member of the group. That just convergent evolution can mess things up with identifications that way too. So
Right.
as you go further back in time, it's harder and harder to identify it. Yeah. But I wouldn't be surprised. Let's see. So I said this was teeny. Let's look for scale. So Brachycephalus is a living frog taxon here, but this is deceiving, obviously, with no scale bar. So we can shrink down our specimen so it's about the same size as that taxon. But let's get perspective on how big that actually is. And it fits on the end of your finger. This is a tiny, tiny little frog. So our Triassic one is probably about the same size as that guy.
That's unbelievable that you found that.
Yeah, well, you know, a lot of it is the search image that you have. So earlier in the talk, I was saying how mostly what we knew from the Triassic is from the late Triassic and from really big animals. And this site that we've been working is somewhere where we sit the whole day and you're just breaking rocks open and kind of staring at them. The preservation is really good for preserving these small fossils in the first place, but we're also taking the time to look for them. You could really easily just go through this place and pick up the big Aedosaur plates and the Phytosaur material and have that be your story still, but that's not paying attention to all of the detail that's there. You know, when you actually focus in and you look at the ground, it's amazing how many fossils are here. Yeah.
So if you wouldn't mind, if we could get to sort of what are the main highlights before we move over to the audience's questions. So, you know, I know there are some first aspects to this, right?
Sure. So our distribution from before, we had 250 million-year-old frogs and 185 million-year-old frogs. But with this new Chinle specimen, now we have something that kind of breaks that up. We have a 215 million-year-old frog. It also shares a lot of morphological features with living frogs. And so we can say that we've got kind of that more derived morphology already present by 215 million years ago. And now again, by knowing that these are here, we've modified our search image in subsequent field seasons. And so now we have several specimens of this. And the end of this one, if you look at the kind of for your perspective on the right side of it, that's the front end of the ilium. And it's a little bit crushed in that first specimen that we found, but some of the other specimens that we've recovered are not. And it shows us that the hopping behavior was probably present in this taxon as well. So we can pull that behavior further back in time, not just that the clade was present.
And the equatorial aspect, I guess that's interesting too.
Indeed, yeah. So we're not quite sure if that's an actual, like a biogeographic signal of where they're diversifying, or if it's just a preservational thing with the Chinle Formation being so fossiliferous and preserving all of these small fossils as well as the bigger animals. Yeah.
Mm-hmm. David, I guess we should probably check and see what kinds of questions we have out there.
Sure. If people want to start asking questions, you can go ahead and, like I said before, put them in the chat next to the YouTube video. We have a live chat running. And as I mentioned before, if you have a question and you can't leave it in the YouTube chat, go ahead and go to the Gray Fossil Site Facebook or Twitter page and send us a message there, and we'll check there. And we can, once people have sent in their questions, we can start taking those. I actually have a question.
Sure.
If I can ask you one. This is a bit related to what Blaine was asking before. We're talking about sort of early frog distribution. Do we have a good idea of where frogs came from? The ancestry of frogs, or the ancestral geography of frogs?
Just in terms of the geography itself, or in terms of their relationships?
Their relationships is really what I'm curious about.
Well, yeah, us too.
Okay.
So with those early members, the early Triassic frogs, I said they look really similar to salamanders, but the relationships among amphibia have been kind of controversial through time, right? Are frogs and salamanders more closely related to each other? And then Sicilians, the sister taxon to those two, Are Sicilians from some completely other group that's in the Paleozoic? There's a lot of different hypotheses about how those modern groups, came about and how they really are related to each other. With the fossils that we're finding from the Chinle Formation, we're not looking old enough really to be able to figure that part out. I think that's going to be for people that are looking more at Paleozoic fossils. We can figure out a little bit more about how some of the more derived members might be related to each other, or when certain features appear. But in terms of like how frogs are related to the rest of amphibians, our fossils aren't really going to help with that.
Mhm.
All right, we do have some questions coming in, and thank you for answering that question. That's, sometimes we don't know is my favorite answer in science.
Yeah, it's never a problem to say we don't know, but we're trying to find out, or go find this other person who's trying to find it out, right?
Right. Every I don't know is a research opportunity.
Exactly, right.
So we got a question here from Martin, who asks, aside from the tail, what are the primitive traits found in these frogs that we wouldn't see in today's frogs?
Let me see if I can. Oh. Now, why does it not want to? Aha, there we go. So we can compare the stem frog, which is kind of based more on like Triobatrachus, with a crown frog or a living frog. This is kind of like your rana, or something that we would find today, hopping around everywhere. You can see some big differences between them. The length of the toes are a big part of this. So like the size of the hands and the feet are different. But the big one for us is the number of vertebrae in the backbone gets really reduced in living members of frogs. And then living frogs have this structure, part of their pelvis called the urostyle. So that's this midline structure, and it's just a big rod. It's really interesting how it develops. And there was some research out of the University of Chicago recently that talks about how there's a dorsal part of it and a ventral part of it that fuse together through ontogeny. So I want to look into that a little bit more here. But that big rod of the urostyle is matched in length by the ilia, or that part of the hip bone. So this huge extension of the pelvis is something that really characterizes those living frogs today. And we don't see that in the earliest frogs. So that's one of the big changes of the group. Another one is how lightly built the skulls of most living frogs are. They reduce a lot of their bones and lose some, or they fuse some up. A lot of that then is space for muscles. But more stem frogs have a little bit more ossified skulls, or more bony skulls. There are some frogs today that are very kind of quote unquote bony, I suppose, but they are kind of doing that secondarily.
All right. So we have another couple of questions here from Grant, who is one of our former students here at ETSU, who asks, has the frog material that you're collecting been mainly recovered through screen washing, or is it through eyeballing the outcrop?
It's almost entirely through eyeballing on the outcrop. We find it when we're sitting on the ground. A lot of our material, remember those teeth that we would screen wash, the water ends up splitting them in half a lot of times. So most of our material now from this site, we don't screen wash at all. We actually will collect it as big chunks, or try and get the, small little blocks of that jaw, or that whatever, the ilium, if it happens to be a recognizable frog bit, out. We'll try and get that out in the field, wrap it in toilet paper and protect it, and then bring it back. But if there's something, this site is pretty ridiculous in terms of the amount of fossils that are there. And so we'll do micro prepping in the lab then, and do it under the microscope so that we can be really careful with that. So we almost don't do anything with water with this site anymore, because it just disintegrates stuff.
And then a related question also from Grant, have you found any early salamanders in the Chinle?
Yeah, it's unclear. With salamanders, it's a little bit more difficult, at least for me, because there you're looking at the vertebrae, I think, to be the most recognizable part. Or if you're lucky, you might get some skull material or some parts of the jaws. Telling the skull and jaw material apart between a frog and a salamander, that's something I have a hard time with. The vertebrae would be the easiest there, but again, those are super delicate. And so it's likely that we've found some and collected it and just haven't been able to recognize it yet. And I think that's probably true of more parts of the frog skeleton too. Like we use the ilium as kind of the basis of the discovery of this Triassic frog or this chinley frog, but I'm sure that there's other material there that we just don't recognize. And we probably collected it and it's under bone fragment, or it might be under fish or something like that. And so that's why, that's part of why I think it's so important that my students take the bones class and learn how to recognize these things, at least in extant animals too, so that then you can get a better sense when you're looking at these fossils in the ground. All right, you had a chance in the classroom to look at this very nice, normal looking skeleton with all its parts and in the right order. Now let's smash it up and then spread it across and mix it with 3 other species and try and figure out what it is you're looking at, right? That's field work.
Is this really the first dive into looking at the microfauna of the chinley?
We started doing it, I think, when we found this site, really. So kind of a broad brush strokes of it when we discovered this green site, we call it, because the layers are actually like green and white, kind of micro banding there. And just because of the sheer number of teeth that were there, we started paying attention to what was there. And we realized, oh, it's not just teeth, there's small bones as well. And so we for the past 5-6 years, whatever it's been now, have really been focusing on those small materials, because early members of many groups start off at small body sizes. And so if you want to understand the early diversification of these clades, you have to look at small things. So I'm really out of my kind of comfort zone here with my gigantic phytosaurs looking at tiny, tiny bones now. But that's where you're going to find these things. It's, you know, if you want to find a mammal, you have to look at their tiny little teeth. If you want to find a frog, you have to look at their tiny hip bones or look for their vertebrae. And then the Triassic is full of these crazy weird things that aren't just big rausuchids and aedosaurs and phytosaurs. There's a lot of really strange small-bodied animals. And so you got to pay attention to microfossils. Yeah, so we've been doing a lot of that the last couple of years.
So we've got a handful of questions. Let's see if we can get through 1 or 2 more here real quick. While we're on the subject of frog anatomy, Barbara has asked, which part of the frog skeleton shows you that it was a jumping creature?
Ah, good question. So on that hip bone, there's, let me go back here and I can, do 1 more back. There we go. Okay. So there's the acetabulum kind of in that rounded dishy part there. And that's where the upper leg bone or the femur sits. So that's the hip socket. And we all have that too. That's how you can actually move your leg around. Then there's at the other end of it, this frog ilium becomes a tube that shoots out there. If this specimen was totally beautifully preserved, that tube would continue just a little bit more. And then on the inner surface of it, so the side closer to the midline of the body, there should be kind of a little like rocking joint almost where it connects with the vertebrae. So that articulation point or that joint, because of the way that it is, the way that it develops, it can kind of move. And so that surface is what we look for to indicate whether or not that frog could jump. So this specimen didn't necessarily show it to us because it's crushed there. So we try to be pretty conservative and say it maybe, it looks like it is, but we're not quite sure. But other material that we found now is a little bit better preserved. And we've been micro CT scanning everything that comes from this site. So then we don't have to prepare it and we can preserve it really carefully in the rock. But you can see all sides of it then, and then you can 3D print the models of the specimens themselves and look at it super huge if you want to. So we can see that some of the other specimens that share the same features of the acetabulum and the kind of more proximal parts of the bone also have that rocking joint distally.
All right, I think that we'll stop taking the questions there for now before we end the official recording. So we're gonna wrap up the official portion of this presentation here in a minute. But if you have more questions, if you've already asked more questions, we will continue to share them with Michelle and see if we can get some answers for you. Blaine, if you have anything else you want to say, go ahead.
Oh, thanks again, Michelle, for being on the show.
Thank you.
That was fantastic. Is there anything else that you wanted to say before we stop the recording?
I would say that all of these specimens that we're collecting, they're going to go into museums so that other people can study them. It might take a little while because preparation takes much, much longer and study takes much, much longer than the actual collecting of it. But we're trying to preserve this material so that other people can look at it. So natural history museums are kind of getting hit hard right now with layoffs and with people not necessarily being able to visit and everything. But those museums are repositories for understanding current life because of the past life on Earth. So we need to support those museums and make sure that they're there for future everybody, not just future scientists, but for everybody to understand our place in the world.
Thank you for adding that. All right. See you next week.